Hello, everyone. Thank you very much for joining my presentation for this 2024 edition of Cosmology from Home. Today, I'm going to talk about a study that we did in collaboration with Tiago Barreira and Nelson Nunes from the Institute of Astrophysics and Space Sciences in Lisbon, Portugal. And this work was recently published in PRD, and it concerns the cosmological variation of the neutrino mass. And the aim was to see whether a neutrino with a growing mass receiving energy from a scalar field dark energy could relax the existing constraints on the neutrino mass, which are obtained with the measurements of the cosmic microwave background. And I would like to start by recalling that the standard model of hot Big Bang predicts that the universe is filled with a background of relic neutrinos, which is yet to be detected. The thermal neutrinos were initially coupled with charged leptons through weak interactions in the early universe, in the primordial plasma. And as the universe expanded, its temperature dropped below 1 MeV, and the neutrinos decoupled from the plasma because the weak interactions became so rare that they couldn't maintain the equilibrium any longer. And since then, neutrinos have been free-falling along the geodesics of spacetime. And the key thing to stress here is that the neutrinos were ultra-relativistic when they decoupled, but we expect that one species of neutrinos was non-relativistic at the time of the emission of the CMB. And this feature has cosmological implications, since the neutrino background contributes to radiation at early times, and it contributes to matter at late times. And also, because they were relativistic at the time of decoupling, the neutrinos have maintained a Fermi-Dirac distribution, and therefore they were not subjected to Boltzmann suppression. And this is why we expect that relic neutrinos are very abundant today, and this is why we can do neutrino cosmology. So after the positron electron annihilation, photons were hotter than neutrinos because the neutrinos are already decoupled from the plasma at the time of the annihilation. And the ratio between the two temperatures can be computed from entropy conservation. And the temperature of the photons is well measured from the CMB, which in turn gives the current temperature of 1.9 Kelvin for the neutrino background. And this 1.9 Kelvin corresponds to a significant present-day density per neutrino species that you can compare with the 400 photons per cubic centimeter. So we expect that the cosmic neutrino background has a temperature and it has a number density of the same order of magnitude as the CMB, but it is clearly much harder to detect. We also know from flavor oscillation experiments that the neutrino is not massless. The neutrino is a massive particle. We have to define effective masses because the free flavors are not mass eigenstates. They are rotated in mixing angles. And while we don't know the absolute mass scale, the difference between the different masses can be probed by solar or atmospheric oscillation experiments. And there are two ways of arranging the hierarchy between the masses, the normal ordering and the inverted ordering, which lead to two different lower bounds for the sum of the masses. And those bounds indicate that at least two neutrino species are non-relativistic today. And the lower bound on the mass sum implies a lower bound on today's neutrino energy density. But it also works the other way around. If you have an upper limit on the energy density coming from cosmological observations, you can derive a maximum value for the neutrino mass. And this limit was originally derived in the 60s. The simple requirement that the neutrinos do not overclose the universe suggests a cosmological constraint below 100 eV. And this constraint was far stronger than those obtained in the lab at the time. And today, it is the Planck measurements of the CMB that provide the most robust constraint for the standard 7-parameter model. And this limit can be even strengthened by combining the Planck data with probes of formation of large-scale structure. And this limit is still stronger than the laboratory constraints, like those of the Catherine experiment that measures the tritium beta decay. And in fact, the DAISY collaboration recently obtained a substantial tightening of the upper limit from measurements of baryon acoustic oscillations in galaxy, quasar, and Lyman alpha forest tracers. And the DAISY bound is about 0.072 electron volt, which is very close to the lowest bound obtained from flavor oscillations. And in the future, we might be facing possible tensions in the neutrino mass determinations between cosmology and experiments on Earth. But this upper limit coming from the cosmological probes is model dependent. It has been derived in the context of the lambda CDM model, the standard model in cosmology. And people have been investigating alternative cosmological scenarios, including modified gravity theories that may relax the neutrino mass limit. And there is, for example, a model which possesses 5 extra parameters that weakens the limit by a factor of 4. And in our study, we adopted a similar approach, extending the parameter space, but with only 2 extra parameters, which describe a possible interaction between the neutrino fluid and the dark energy component given by a scalar field. And the originality of our approach lies in the choice of the parameterization for dark energy, where the value of the scalar field linearly depends on the number of electrons. So we have introduced this parameter lambda as a rate of change in the scalar field. It's the slope of the scaling with the number of electrons. And this parameterization, which was first proposed by Nunes and Lindsay, can reproduce the cosmological history with just one additional parameter. And this parameterization has the advantage to represent a vast class of dark energy models that rely on scaling or tracking solutions. Because the corresponding scalar potential that can be reconstructed analytically is a sum of exponential terms that attract the universe towards its current acceleration following scaling regimes with radiation and matter, irrespectively of the initial conditions. It is therefore a good alternative to the use of the popular and familiar CPL parameterization, since we reduce the degeneracies in the statistical analysis by limiting the number of additional parameters. And as for the interaction, we went for a constant coupling beta that can be interpreted as a conformal transformation, where the massive neutrinos are free-falling along the geodesics of a different metric, which is conformally related to the gravitational one. And the coupling leads to an effective neutrino mass that depends on the value of the field. The stress energy tensor of the neutrino fluid and of the scalar field are not conserved separately. We have a source term in the continuity equations that depend on the 2 additional parameters of our model, and which also depends on the trace of the neutrinos. And this means that the coupling only kicks in once the neutrinos cease to behave as radiation. And we can see in this plot of the equations of states that the scalar field here in black first tracks radiation when radiation dominates the background. Then it tracks matter when it is matter that dominates, before being attracted to the late-time acceleration phase of the universe. And as regards the neutrino fluid in orange, it behaves as radiation initially, and then it behaves as matter after a non-relativistic transition whose redshift is controlled by our two additional parameters. And we have modified the Einstein-Boltzmann code class to implement the model at background and perturbation level, to study the signatures or to study the imprints left by the variation of the neutrino mass in different observables. So regarding the linear matter power spectrum, the scalar field itself suppresses power on the small scales for a vanishing beta. And this suppression is either compensated by neutrinos of growing mass when beta is positive, or the suppression is exacerbated by shrinking neutrinos when beta is negative. And this is due to their larger free streaming effects, because below their free streaming scale, the massive neutrinos do not cluster like cold dark matter. They dampen the fluctuations up to a critical scale that depends on the evolution of the mass over cosmic time. And the mass varying neutrino also affects the anisotropies of the CMB on the intermediate scales, which are dominated by the imprints of the acoustic oscillation in the baryon photon fluid. The evolution of the neutrino mass changes the time evolution of the gravitational potentials at the time of the last scattering, and therefore changes the amplitude of the first peak compared to lambda CDM, which is given by the early integrated Saxtorth effect. And at larger angular scales, which are reminiscent of the scale invariant primordial spectrum of the inflationary fluctuations, the additional power produced by the time evolution of the gravitational potential decreases as the neutrinos shrink. And the model also alters the silk damping on the small scales, and especially because the mass of the neutrinos influences the damping scales or the damping scale at recombination. And finally, since the free streaming neutrinos erase the density perturbations, they affect the CMB light, which is distorted by gravitational lensing, by the distribution of matter between us and the last scattering surface in the line of sight. And in fact, the neutrino mass reduces the lensing potential. And since this effect is proportional to the energy density of the neutrinos, we can constrain their mass, whose evolution is again controlled by our two additional parameters. So we tested the model with observations to infer constraints on the parameters. We used the 2018 release of the Planck measurements of the temperature and polarization and isotropies of the CMB, which we have combined with the lensing potential. And we also relied on baryon acoustic oscillations data to help break the degeneracies that exist between the neutrino mass and the expansion rate H naught. And we used flat priors of the 9 parameters that we kept free, that we varied in the MCMC analysis. We obtained 2 main results that are displayed in this plot, where you can see the marginalized confidence contours and probability distributions in the parameter space. So firstly, the model increases the upper limit on today's mass by a factor of 5.5. We confirm the conjecture that a growing neutrino receiving energy from a scalar field responsible for the late-time acceleration of the universe relaxes the upper bound derived in the framework of the lambda CDM model. And secondly, the dynamical property, the dynamical aspect of dark energy is enhanced in this model because the scalar field must lose energy to the neutrino for its mass to grow over time. And with a non-vanishing scalar field parameter, the observational data we used disfavor static field. So it disfavors the cosmological constant at the 1 sigma level. And this result is in contrast with previous work in the literature where it is lambda CDM, which is favored as a cosmological model when dark energy is coupled to dark matter. And in my last slide, I would like to give you some prospects for upcoming work. It would be worthwhile to complement the CMB constraints that the Planck data place on the parameters of our model with precise measurements of the anisotropies at larger multiples. So this is being done by the Atacama Cosmology Telescope. The small angular scales, when they are measured with sufficient accuracy, can reveal coupling signatures, particularly when the strength of the interaction is small. And for instance, the Atacama measurements of the high multiples of the CMB power spectrum have already found evidence for non-vanishing coupling between neutrinos and dark matter, this time at the 1 sigma level. And also, in the future, we expect that combinations of cosmic microwave background experiments with large-scale structure experiments will significantly improve the precision and the robustness of the measurements of the neutrino mass. And this expected improvement might help us discriminate between models of interacting dark energy. So I have reached the end of my presentation. I would like to thank you for your attention and see you and goodbye.